Hello.
Hello, sir.
Yeah, so we shall we continue?
Yes, sir.
Right. So we continue our revision session. So in the previous session what we saw, we extend our discussion today based upon that. So here you see, if you recall from our previous sessions, we talked about the compound logic and CMOS fabrication concepts and so many other points. Even we just revised in previous session. So here I gave you a quiz to design an N input CMOS NAND gate, right? So design a gate which has N inputs. So symbol it would be like 1, 2, 3, 4 up to N input. And what you all need to do is that design a gate, a logic which will perform the function of a NAND gate. So that was the question. So for example, I said, okay, for n equal to 3, I will have 3 inputs to my NAND logic, okay, which is shown, and I want to implement it using the transistor circuit. So I know how the PMOS works, how NMOS works, as you might want to recall. And based on my previous concepts that I learned, I tried to construct this logic circuit which will perform the function of 3 input NAND logic. So what I have here, A, B and C, and I use the compound gate logic. What is compound gate logic? It says that I will have NMOS transistors in series, as you can see here. So I have a 3 input, so therefore A, B, C, I put all them in the series combination. And obviously the Y would be A and B and C bar, or we can also write A and B and C, just put a slash here. It indicates you are complementing these inputs over here. So why needed to be that? So when I see that there is a complementary line here, so it means I have NMOS transistors and then they are in series, so I will have on top of them PMOS, they will come in parallel, right? So this formed a pull up network and this formed a pull down network, right? And this is how I understood that okay, this circuit will work as a 3 input NAND logic. So what I analyze, I have 3 inputs, so total 2 to the power 3, 2 to the power n would be the input combination. So I have 3 inputs, so 2 to the power 3, 8 combination of inputs are possible. So I start with A, B, C, 0, 0, 0, 0, 0, 1 and so on up to 1, 1, 1. And I would then have verification what comes at the output based on what switching happens into the circuit. So we see that when all gates of the input, as the AND logic says, the output of NAND, not the AND, the output of the NAND logic is equal to 1 only when all inputs A, B, C are equal to 1, right? And in that case, not really, it's a NAND logic, right? So output of the NAND logic would be 0 when all of its input are at logic 1, right? And if any of the input is at logic 0, then the output will be logic 1. So how it happens in the transistorized circuit, we saw that the output will be either pulled down to ground 0 or it will be pulled up to VDC. This is VDD, right? And this is how we defined it. And I told you, like, is it possible to, let's say, PMOS transistors are in the series, let's say this is the PMOS network and this is the NMOS network right here, okay? And that's the Y output, here is VDD and that is ground one. So what I'm doing is that just putting the NMOS transistors up position and the PMOS transistor down position. Will it perform the NAND logic? Yes, but the output will be degraded one, right? So always remember NMOS logic should be down for pull down network, and PMOS logic comes up as a pull up network. So that was our understanding about how to construct any logic using the compound transistors. So then I explained to you about, okay, I want to have this logic equation, I want to implement that. So there are two ways to implement that. One is the using logic gate, and one is the transistor circuit. So if I want to ask you implement this logic which says y equals to a and b or c and d, and I have a complementary function. So I can also write a and b or c and d, and instead of this bar I will just put this slash over here. This indicates the function is having a bar on top of it, or it's a complementary. So how I can realize, okay, I see that, okay, there is an AND function, so I will know that there is one AND gate I need. There is another AND gate I will see, then I will put another AND gate right here, C and D, and there is a ORing of these two, so I know that I have to use the OR logic. So OR gate, so basic gates I am trying to. Then I know that there is a complementary, so here I put the inverter, and that's how I will get the Y. So instead of this I am putting inverter in front of the OR logic, so I can also draw this in this fashion, so it's a NOR logic, because I know that OR and inverter is basically a NOR logic. So this logic I implement using AND, this is AND, and this is NOR, or I would say AND or invert logic. So that's the one possible way I can implement this logic function, Boolean function. But I told you, if you remember, we always want to implement the Boolean function, any Boolean function. For example, this is the Boolean function that we are watching. So I have informed you that we can implement any Boolean function always with the either NAND logic or NOR logic. So remember, because they are simple and easy to construct and most straightforward approach, because to implement the NAND non-inverting functions like and here you have OR gate first and then inverter, you always have to use the inverter, right? We have seen that this becomes, so although this looks a very simple form, but finally remember you can always convert this logic diagram into the NAND logic and the NOR logic. So now you would like to recall how you would like to implement this function using the NAND or NOR. Always remember, any Boolean function we would prefer the NAND gate or the NOR gate. All NAND functions and all NOR functions, because that's the most easy and straightforward approach. And then we know that once we have a NAND or NOR logic for any Boolean function, we go to transistorized implementation. We know how to put the pull down network and pull up network. So now I leave it to you to, the question is how to use NAND gates to implement such Boolean functions. So you have to recall your basic Boolean algebra that you might have studied in your undergrads and the graduate studies. Use the De Morgan's law, complementary, and there are other basic functions, right? Just recall your concepts using truth table and K-maps and all that. K-map is not required, but just recall all those Boolean algebra concepts. That will give you answer, or refer some books that will give you answer how to implement any Boolean logic using NAND or NOR. Okay, so the question here is, once we know how to implement any Boolean function using logic gates, for example NAND or NOR, now second task is to implement them using the circuit diagram. So circuit diagram is, we use the logic of compound gates. Compound gates or we say that compound gate, it means we have NMOS as well as PMOS logic. So what we do again, I have a AND function. So I know that two transistors NMOS in series will help me to implement NAND. Then I have another AND function. Then again I will take one more pair of NMOS in series. Then these two AND, this X and Y, let's say, they are ORing with each other. So ORing means I will put these two individual pairs in parallel like this. You see, they are connected in parallel. So this is basically my one network. I want to create a complementary of it using PMOS transistor. So what I see, A and B NMOS are series, so I will put A and B PMOS in parallel. C and D NMOS are in series, so I will construct C and D and PMOS in parallel. Now these two pair got in parallel with each other to create this A dot B, A and B, or C and D. So I will do these two pairs and put them in series. So you see, this is a pair number 1, this is a pair number 2, and they are in series here. So this is another network. Once that is done, you have network number 1, you have network number 2. We come here, we see that this is the network number 1 using NMOS, this is the network number 2 using PMOS, and PMOS is put on top of each other. So here is my VDD, here is my ground, and now we know that this is basically A and B or C and D bar. Okay, so this is how I can design a circuit. I know that the upper network right here will act as a pull-up network. Always remember that using PMOS transistor, this network right over here will act as a pull-down network. Always remember that, right? What if I swap the position of these two? I will still get this function done, but output will be degraded one. I want strong VDD logic 1 and strong 0 logic 0 right here at the output. That's what I want. So to summarize, what we say is that this was the first function I gave you for the exercise, but now we know that any Boolean function, if anybody asks you to implement a Boolean function, any function, y equals to a or b complementary into c with d bar, something like that, with multiple number of inputs, always remember you have a simplest implementation. You know that a or b, I will have logic a and logic b, and this is a OR gate. Now there is a bar, so I will put inverter here. Now that's the one thing. Then it's a AND of, so I have another input C here, and then again AND here D bar, so I have D here, but I need to invert it. So once that is done, I see that this is a ANDing, so at the Y will be equal to this function. So this is the simplest function. You see that there is a OR gate, inverter, and the AND gate. But remember, you would like to implement this logic only using NAND and the NOR. So again, how will you do that? Refer to your Boolean algebra basics, De Morgan's theorems, and other Boolean laws, and with that you will know how to implement this using NAND and NOR. Now this is the simplest Boolean function, but what if you have 10 inputs and there are many gates, let's say hundreds of gates, and that circuit is a Boolean function doing specific digital circuit. So how will you use that? You will take the help of EDA, that is electronic automation design tools. So once you write the HDL verification code, you will write the hardware description code using transistor netlist or the structural description, and then you will feed it to the tool. The tool will synthesize your multi-input logic and many gates that the circuit has, and it will automatically implement your logic functions not using these basic gates, but it will implement using NOR logic and the NAND logic. So you don't really have to worry about that. As an engineer, that's the job of a tool. It has many input logic function, and it has multiple gates. It be hundreds and thousands. So that's the job of a tool. But as an engineer, the basic task still remains to you to mathematically understand by means of this basic logic I explained you how things are happening, how the logic is constructed, both at the gate level and at the circuit level. So having said that, look at this logic diagram, how it looks. I have A, B and C, D, 4 inputs. That's the AND, that's the AND, and I know that this is a NOR logic, right? So I will call it as a AND NOR logic. And earlier, if you remember, I had told you this was AND or invert logic. Okay, so this is how you do that. So example number 2, just to remember, again I have A or B or C ANDing with D. So your task as a designer, as a logic designer and as a circuit designer or as a layout engineer, to analyze, can you simplify this further? So again, apply the laws of Boolean algebra, De Morgan's theorem and other laws, and always look for whatever the function is given to you, can you just apply those Boolean algebra and to simplify it further. And once you analyze that, okay, this is the final form that you want to implement, it cannot be simplified further, because what is the advantage of simplification? If you simplify it, you reduce the number of inputs, you reduce the number of bars, so it means it is easy to implement with the few transistors or the few logic gates, right? So again, you want to draw the logic gate, so obviously you would go for A, B, C, you have OR function, then you have an AND logic here because this function is ANDing with this, so this is D input, and what you do here, you have AND logic. So obviously Y would be final output. So this is AND NOT. So replace this with the simplification would be, replace this with the NAND. So you have NAND here, you have AND here. So this is AND or AND NOT, or simply say AND NAND logic. But what was my saying to you? Or you will look for to implement this logic function using only NOR gates or NAND gates. Remember, when you have the NAND logic implementation, take the complementary of it, it will have the same function you will realize using NOR logic, right? Again, Boolean algebra. So you would prefer to implement using NAND and NOR because that's the most simple logic. Okay. So look, how will you go for the transistor implementation? Again, I see that A or B or C. So A or B or C, it's a OR logic, so I will place NMOS switches in parallel. Then AND comes, D input comes with the AND. So I know that there is a D input, but this switch NMOS will come in series with the parallel combination of these three switches. So my down network, which I called as pull down network, is ready. I just want to take the complementary of that. Why? Because there is a bar here and this is a CMOS logic. So CMOS logic will always contain NMOS and PMOS. So what I do, ABC were series, were in parallel here. So I took ABC PMOS switches in series. Now D was in series with this parallel combination. So D PMOS got in parallel to these three, and that's how I got the output function. So remember, now you would always have, you can now implement any Boolean logic using logic gates and using transistor implementation. Once your logic gate concepts are clear, you know how to implement any Boolean function, multiple inputs and many gates, no matter. So first task of you as a logic designer will be multiple inputs and many gates it has. So to try to optimize it, optimization means you will try to apply Boolean algebra laws and simplify the functions. And final, you will go for NAND implementation or NOR implementation. Using that, then you will create a transistor circuit. This was the exercise. You are asked to draw the output network for this logic function. How will you do that? I see A or B or C and D. So how do I do it? A or B. So using transistor I want to do that now. I know how to do it using logic gates. And once I draw this function using logic gates, I will use Boolean algebra laws, simplify it and use the NAND gates only or NOR gates only. But now how to do it with the circuit diagram? So simple, A or B. So I have two switches here, NMOS, A and B. Then I have C and D, but there is something wrong here. I have done A or B means they should be in parallel because NMOS switches A or B. Now C and D. So let's say I have C and D. That combination is C and D. This is ground. This is ground. And now there is a ORing between these two functions. So there is A or B like this in parentheses. So ORing means they are in parallel. So it's just like that. And here was the output. Once that is done, what I can take is the complementary because there is a bar here. So simply A or B are in parallel. So I will see that PMOS A and B, they are A and B, they are in series. Now these two combinations are in parallel. This network and this network, they are in parallel to each other. So I will take in series with this. I will put them in series C and D. C and D are in parallel again. This is C and D are in parallel, and these two combinations are in series actually because they are in parallel. So what I do, let's say I erase this here and I will use this one C and D. This is C and that is in series. This is how it is, simply way, right? And this is your VDD. So just try to understand how I have connected. You can rearrange this to show the proper circuit diagram in a proper format. Okay, so just for your understanding. Now in another exercise here, it was I am asked to write the output function here. What is going to be the output function? So what I see here, this is the PMOS transistors pull-up network. This is the NMOS transistor pull-down network. So what I write here, first function is A or B. I start with the NMOS, A or B. So A or B, and in series with that I have C and D. That's it. Once that is done, I know this is complementary, so I will just simply put the bar. So you see now, this is how you will write any output function for the given network, or you will draw the output network for the logic function. So this is basically the task of an engineer to analyze the circuits. Then we talk about the spatial gate. We talk NAND logic, NOR logic and inverting logics. What about another gate? We call it as a transmission gate because it transmits, it helps to transmit the bit information. Information could be logic 0 or logic 1 from one point to another point. Or another name of it is the pass gate. I call it as a pass gate. Pass gate logic. So what I see here, first of all, I know that this is my NMOS. This is, let's say, my source. And this is drain. And this is gate. So source can be at logic 0 or 1. And when the gate is enabled, this act as a closed switch. So it's just like it's like closed switch got closed, so source connects to the drain. So 0 or 1 logic which was present at the source, that gets available at the drain, right? So it's simply a switch. And for the PMOS also, I have the same understanding. When the gate, which is a control input, is closed, so it acts as a switch, and the source, whether it's at logic 0 or 1, this information is passed on to the drain. So that's how my switches act. But there is a problem here. I have told you that NMOS passes strong 0. Strong 0 means strong logic low level. It means output will be at logic 0, not at the degraded level. PMOS passes strong 1. Okay, but I told you that NMOS passes weak 1 and PMOS passes weak 0. This is the reason I just told you that to remember these laws simply. So NMOS is a good switch to pass 0 from input to output, but it is a weak switch to pass logic 1 from input to output. On the reverse, PMOS is a good switch to pass logic 1 from input to output, but it's a weak switch to pass logic 0 from input to output. And this was the reason I never suggested you to connect NMOS at the top. For example, this was the circuit we talked about, VDD, and this is the inverter, and Y will be A bar, but it will be degraded output. Whenever you have a 0 and 1 here, it would be 1 and 0, just inverse of the input, but degraded level. It would not be a logic 1, it means it's not the full VDD, and logic 0 means it not the full ground, the degraded outputs. Why? Because PMOS is poor in pulling down the output to the full ground. It will always be above the ground level. This is the ground level, which is 0 volt. Okay, logic 0, but it will be, let's say, 0.1 volt or something like that. Why? Because there is a concept. And similarly, before I explain that, similarly NMOS will always be functioning poor to pulling the output to the full VDD. VDD is the strong level, that is what we want, but it would be somewhat less than VDD. Let's say VDD minus VTH. Now what is this VTH? VTH is threshold voltage. Threshold voltage of a transistor. So what is the threshold voltage? So I just remember one thing. Whenever the transistor gate is connected to logic 0 or 1, based on what transistor it is, there is a certain amount of logic, or let's talk in terms of voltage. Whenever the gate is connected to a voltage, to turn the transistor on depends on positive voltage or negative voltage. Whether I am connecting the gate to the positive voltage or the negative voltage depends on what is that NMOS transistor or that is a PMOS transistor. So for the NMOS case, let's say I turn the gate voltage to the positive voltage, but there should be a sufficiently high positive voltage to turn this transistor on. So that is called as threshold voltage. Okay, below that threshold voltage, although gate voltage is positive, the transistor will not be fully on. Okay, so just remember that, just like in a PN junction diode, you know that there is a diode, you have anode and you have cathode, right? So you know that there is a turn on voltage for a diode. For the silicon diode, how much is the turn on voltage? For the silicon diode, 0.7 volt. Yeah, 0.6 or 0. So always whenever you apply voltage to this network, let's say, the diode will act as a switch and diode will turn on only when you cross this breakdown voltage of a diode. Similarly for the transistor. So always remember there is a voltage that's called as turn on voltage, or simple words, threshold voltage.
Sir,
So
one more explain, sir.
yeah, what is the question again?
one more explanation of
For the
the diode, sir.
diode, okay. Diode, we know that simple silicon diode is the p-n junction, p and n. You have anode, we call it, this is cathode, and what we do here, we connect the positive voltage to the p and negative voltage to the n. So this is p type and this is n type. So what happens? Positive voltage. So because of this battery level, your diode is forward bias. So when the diode is forward bias, the circuit is complete, the current flows, right? And this voltage should be greater than the cut-in voltage or turn on voltage of the diode. So if I apply 1 volt, then it will overcome the 0.6 or 0.7 of this silicon PN junction, and then I would say the circuit is closed, diode is forward bias. But if I have P and N and anode and this is cathode, and I have a reverse voltage, let's say I apply a negative 1 volt. So what happens here? This is a reverse bias because P is connected to the negative and N is connected to the positive voltage right here. So diode acts as an open switch. So there will be no current flowing through the circuit, and we say that diode is reverse bias because this voltage negative 1 volt is less than 0.6 or 0.7 positive voltage, right? So this is how the diode acts as a switch. Similarly, the transistor also acts as a switch because the voltage you applied to the gate has to overcome certain voltage. Is clear?
Yes, sir. Yes.
So we saw the drawback of NMOS. It passes strong 0 but passes weak 1, and PMOS passes strong 1 but passes weak 0. So how to overcome that drawback? Because if I have a logic 0 and 1 and I want to pass it from one point to another point, so it's just a data transmission, right? So I want a strong switch which will pass both strong 0 and strong 1 to the output. So another gate that I am calling it is a pass gate or transmission gate. So what I do, how to pass logic 0 and logic 1, which are both strong levels. So I have an PMOS, you see here, and in parallel to it I have NMOS. So this is say source and drain, this is also source and drain. So you see now PMOS is indicated by bubble, NMOS is indicated as usual. I have an input which could be carrying the bit of information of 0 and 1, and it reaches to the output when I have a proper signal at the control. So what should be the control? These are complementary. It means if whatever logic level I have here, opposite of that will be available here. Or let's say we start with this one, control at the NMOS, opposite of that will be control at the PMOS. Just bubble means complementary always. So if I apply logic 1 here, it means NMOS turns on. If gate of the NMOS is at logic 1, it means gate of the PMOS is logic 0, obviously. So no matter whatever is the input information here, 0 or 1, the switch is, both switches turn on simultaneously and information is passed from input to output. So this 0 or 1 comes at the output without degradation. So that special gate where NMOS and PMOS are connected in parallel is called as pass gate or transmission gate. Where to use this gate? Where there are data buses in the memory circuits, the big circuits that you will implement, where you will see that these transmission gates are used. Here is the symbol. Just remember, I have A, which is the input, B, which is the output, or simple say I want to pass logic information from A to B, and G is the control, and its complementary is also shown here. So that's the symbol. So now there are ways always. So when just like I explained to you, you will implement any boolean logic function using NAND or NOR logic. When I talk about you will implement any boolean function using NAND or NOR logic, it means you are either doing the logic design or circuit design, or your team, they are doing the layout design, right? So when you are doing that, there are multiple inputs to a logic function. For example, in the screen, 4 input CMOS and logic. This is the non-inverting logic. And how to implement that? Again, always go for NAND or NOR. So you will do that. So how to do that? Non-inverting functions, for example, given here. So there are multiple ways to implement that. For instance, let's say this is a 4 input AND logic, and I have chosen 3 different approach, 1, 2, 3 to implement that. So how to do that? Let's say what I did, I just took the NAND logic and then I got this bubbled inverter. This is called bubbled inverter. So if I check, Y will be always A, B, C, D whole bar. It would be NAND logic. Not really. We are talking about AND logic. So it is, this is A, B, C and D. So there are 3 approaches, 1, 2, 1, 3. So I want AND logic here, right? So if you see that this is a NAND and this is bubbled inverter, so output will be A, B, C and D. So that's the final one. Whenever you see these 2 bubbles like they are just on the same line, remember they will cancel each other, right? So it is as same as like ones. Okay. No, not really. You don't have this. This is NAND and bubbled inverter, so obviously, so it would be simply buffer. It is a buffer. It's not an inverter. Yeah, so the first logic is simply converted to this one and one. What about the second diagram? I have used 4 inverters. So 4. So A, B, C and D. So I got here A bar, B bar, C bar and D bar. So again, these are bubbled. This is bubbled AND gate, bubbled AND logic, right? So whenever I see these 2 bubbles on the same line, remember they will cancel each other. So example, I would say that the same A, B, C and D, that's reaching over here, A, B, C and D, and that's basically input to this AND gate. So obviously output will again be Y equals to A, B, C and D, right? Third implementation, I have 2 NAND gates, NAND 1, NAND 2, and then again 2 bubbles on the same lines, 2 bubbles on the same line. So what I see here, A, B, C, D, because there are 4 inputs, so I split it into two inputs. So I got here A, not here because the bubbles will cancel each other. So what I can write here, I can simply write A and B and C and D, and that's how final will be A, B, C and D. That's it. Now these are the 3 ways how you choose and how you arrived at which level to go. Again, apply Boolean algebra, basic laws of Boolean functions, and you know that how to implement this multi-input AND or non-inverting functions using NAND or NOR logics. Now you see that there are 2 levels. This is called as level 1 and level 2 for all 3 implementation, 1, 2 and 3. What are the levels? Levels means whenever you have inputs to the circuit, the logic is passing from input to the output. Logic is passing from input to the output in all 3 circuit configurations. And how many levels this logic, input logic has to cross to reach from input to output, level 1 and level 2. There are two levels of gates. Okay, so based on your design, you choose which design you choose, that will affect the speed of a circuit. Speed, which is the clock frequency, if it has a clock, if the circuit has a clock, or in the reverse way we have covered this topic, we call it as a delay, gate delay. Okay, that's the inherent delay, the time it will take, inherent time, the natural time each gate will take when the switching inside happens, and because of that information is transferred or passed from input to the output. So there are two levels here, 1 and 2. So there is a two different types of delays, delay of this level and delay of this level in all of these circuits. That is the first point. Size, as the logic and the common understanding says, and we can ourselves think that, okay, if I have how many gates here I have? 1 and 2. How many gates I have here? 1, 2, 3, 4, 5. 1, 2 and 3. So which is the compact implementation? First one.
First one.
Right, so designer also, physical designer or layout or logic designer or circuit designer will always talk about speed. They will want the faster circuit, they will want the circuit or the logic smaller in size and power also. So if you have less number of gates, therefore the less number of transistor, obviously the energy required to perform the logic will be small. So Tristate, this is the another word that we talked about. Tristate. What is Tristate? I know I explained you that there are two states, logic 0, logic 1, and there was another state, I call it as a high Z or high impedance. So I told you that given the circuit, let's say you have this circuit, and I know that this is the circuit is performing the function of inverting the logic. Whatever 0 or 1 here comes as comes at the output, and there I know that at a time only one switch is on to perform this function. But what if both are off? Both switches are off. Right? And here is my output. In such situation, I call the output is floating, or there is a high impedance state. So usually as a circuit designer, you will tie this output in such situation either to VDD or you will tie to the ground somewhere in the circuit. You will do that. Right? So otherwise if it is floating, so you can say that state is third state. One is logic 0, second is logic 1, and third is high impedance state, high Z. So I know that this circuit acts as an inverter, but what if I want a circuit that will just give me Y equals to A? I don't want to complement that. So it means I have a circuit, information is here, logic 0 or 1, and output should also be A, logic 0 or 1 when the circuit is switched on. So that circuit is called as buffer. Right? So we'll see how the buffer works. So here is the symbol. I have input 0 or 1 can be a logic at the input. Y would also be A, that means 0 or 1 will come only when there is one control here. That control I call it as a enable. Right? So when the enable is on, it is also a logic level. Some signal is coming, it is also 0 or 1, depends on what logic you are using. So when it is 0, the circuit or buffer is on and the information is connected to the output. When the enable is 1, you can say that circuit is off and information cannot reach to output. right? Depends on that. Sometimes you show the symbol like this, you have enable shown, and just show its complementary also with the bar, right? So how to understand this truth table? We've seen that. Let's say enable, it means you can always show its complementary with the bar. So it is 0. So in that case, whatever the input 0 or 1, output is at high impedance state. Why? Because circuit is not switched on. The circuit inside is not switched on, so output is floating. So in that case, you say that output is at the high impedance. But when enable is equal to 1, it means its complementary will be just 0. So whatever the input 0 or 1, that will get connected to the output. So this is how the buffer acts. So remember, CMOS inverter and CMOS buffer, Y equals to A bar, Y equals to A. Okay, in inverter you have logic 1 and logic 0 when input is at 0 or 1 and you don't have any control signal. But if both NMOS and PMOS in CMOS inverter, these are switched off at the same time, then you would say the output is at the high impedance state. That situation can happen. So let us see the similarity between a pass gate or transmission gate and the buffer, Tristate buffer. Look at the symbols here. We have input A and the output Y. Input A could be 0 or 1. Output accordingly would be 0 or 1 because NMOS and PMOS are connected in parallel, and this switch, the both transistors switches on simultaneously. Okay, when enable is equal to 1, it means its complementary will be equal to 0, and the switch is on. At the same time, both transistors are on, and the logic at the input 0 or 1 passes at the output. Same is true for the buffer. So both have the same function, right? Look at the truth table again, same. What if in the transmission gate, when the output will be high impedance? When enable is equal to 0, the circuit is both switches are off. It can happen right here, like I explained you, both switches and MOS and PMOS, they are off and the input is available here, but it's not switches are off. Therefore I would say in that case the Y is at high Z, or it's floating. Okay, so remember that. Only when I put some control here equal to 1, the switch, because when it is 1 it means automatically it is 0. I know that switch is on and the Y will be connected to 0 or 1 based on what is available at the input. So I want to make some changes to the basic inverter circuit I have learned. For example, I know this is the inverter circuit, VDD and the ground. That's the output Y, is the input. I know how it works. We know that. So look at this circuit now and this circuit. What changes you see? I just made a little bit changes. I put 2 extra transistors. I have this VDD here. I have ground here. And same input A is here, output Y is here. But this is the upper transistor PMOS and this is the NMOS. And in between I put 2 extra transistors and their gates are connected to enable and it's complementary. Why I did that, I will see in a moment how this circuit will act, right? So for example, if enable is equal to 0, what is the state of this NMOS? We know that NMOS with gate input connected to 0 is switched off. So if NMOS is switched off because enable is equal to 0, enable bar is equal to 1, and for PMOS 1 at its gate will also make it off. So these two transistors are off if enable is 0. So how the circuit will look like? This first configuration. Look at here. How this look? Both switches are off. So look, I have 0 or 1 at the input that wants to get to output, but I'm not doing any switching action because the control, the enable control is switched off. I haven't switched on the circuit, and the control to switch on the circuit is enable. So where enable is equal to 0, I would say output is floating. I don't know what logic it is at. It just, so I will say that's at a high impedance. But what if enable is switched on to 1? So this transistor will be on, enable bar will be 0, it means this will be also on. So this is the second set. This is the first, this is the second case. The circuit looks like, look, both switches are closed. So this circuit is nothing but this circuit now. Can you see that? And once that is done, I have 0 or 1 at the input A, that will come inverted 1 or 0 at the output. It's a complementary of, this is how the circuit will work. So such circuit with, this is the simple CMOS inverter, and this is the circuit of Tristate inverter. This is called Tristate inverter, right? So again, what is the difference? In CMOS inverter, you have only two states, logic 1 and logic 0. Only when you force both these transistors to switch on at the same time. But how will you do that, right? It's not possible because you have only one input here. So when you apply 0 or 1, that input goes to both the transistors at the same time. You don't have two separate lines for the input. It's like in this circuit, right? So you have logic 0 and logic 1. Only accidentally somehow both transistors switched off. Then only your output is at high Z. Otherwise, just say you have two input. But this is special case of inverter where we see that you have two lines now, and with this you actually can force the circuit to go into high impedance state. Okay, so you have a control. So how to generate this signal? Always in this signal, in this circuit, you will have to generate this, how to get these signals. Okay, this A is coming from somewhere, 0 or 1. Okay, and this one. So these signals can be generated internally. So this is called as cell. So as I said, if you are doing the circuit design or physical layout design, you will have a library. So in the library you will have these unit cells, cell of NOR gate, NAND logic, cell of tri-state buffer, okay, cell of simple inverter. So as a designer, you just take them and put it on your screen and connect such cells to each other to create a bigger logic or bigger layout, right? So this control, remember, enable and enable bar, they can be generated within the cell. You have another circuit design that will generate this EN and EN bar separately. Okay, this is another circuit. So you have to draw the layout for this circuit also. Okay, so now there is a multiplexer. So far we have learned that the concept of inverter. We'll also learn the concept of multiplexer. Can anybody tell me if they have a doubt to understand the difference between inverter and the tri-state inverter? Any doubt you see, or whatever I explained, are you in a position to understand that so far? Just a minute. Think about that. Are there any questions so far? Okay, so multiplexer. What is multiplexer? So sometimes if you are designing a memory or drawing a layout of a memory or any data circuit where data wants to reach from input to output, just like in transmission gate we saw that. There is one more block called as multiplexer, or in short MUX. So their use are in the memory or the data manipulation or data transmission. So how to create such logic at the gate level or at the transistor level, right? So we'll understand that we'll use the transmission gate or pass gate to form the multiplexer. How the transmission gate looks like, we know that 0 or 1 at the input, it reaches to output when the switches are closed both. So now this is a single switch that consists of NMOS and PMOS, and that's the symbol. So how to use that? So I have used two transmission gates. This is 1, this is 2. So I know that I have a signal S at the gate of this pass gate, and the same signal, this is the control actually, is applied to the PMOS of another pass gate, right? And when I have a control signal, I will always have its complementary S bar. So look how S bar is connected. It's to the PMOS here and it goes to the NMOS here. So how can I understand how this circuit is working? Multiplexer means, look at the signal symbol. It says I have two data bus or data lines, D0 and D1. They are my data lines. So I want to choose multiplex. What multiplexer does? Multiplexer connects the data line to the output one at a time. And how will I choose amongst these two which one to connect to the output? Based on the control logic. So I will say, okay, if the control logic is 0, connect D0 to Y, and if the control logic is 1, connect D1 to Y. That's very simple. Okay, again, when S equal to 0, connect D0 to Y, and when S equal to 1, connect D1 to Y. So this is how the circuit. So S equal to 0. S equal to 0. It means S bar is equal to 1. Can you understand how the circuit will work? Which transmission gate is switched on and which transmission gate is switched off? S equal to 0. It means S bar equal to 1. So this transmission gate is switched off and this transmission gate is switched on. So D0 got connected to the output. Once again, this is very important. S equal to 0, it means S bar equal to 1. So 1 comes to the PMOS and 0 comes to the NMOS. So this transistor, this pass gate is switched off because I am just not turning on both the transistor. But what about this? S was 0, so PMOS good. S bar is equal to 1 here, so NMOS is also good. So obviously this transistor got on. So I will say D0 connected to the Y. Opposite case, when S equal to 1, this transistor, this pass gate is on, this pass gate is off, and D1 is connected to the output. This is the truth table to verify the function. See here, when S is equal to 0, no matter what logic is available at the D1, either 0 or 1, I don't care. but whatever logic is available at the data line D0, that is getting to the output. Same here, when S is equal to 1, no matter what logic is available at the D0, but whatever is available at the D1, that is getting connected to the output. So that's the basic of 2 is to 1 multiplexer. So how many gates we need to implement 2 data input mux? We need 2 pass gates, and each pass gate looks like this one. Okay, is a combination of NMOS and PMOS. And what's the best advantage? What is the pass gate and what is it known for? It passes input to output, logic 0 and logic 1, which are strong logic levels, both. That's why we use it.